Okay, the next section is 6.5. We're going to sketch some graphs of tangent functions, cotangent functions, secant and cosecant, and we'll look briefly at dampened oscillation for trigonometric functions as well. So first up is the tangent. The tangent has vertical asymptotes at pi over 2, negative pi over 2. I'm not going to be too concerned about that because this is something I'm going to show you that you can figure out, because we know that the tangent function is really just sine over cosine. So you can easily figure out where the asymptotes are because those are whenever cosine is 0. So just look at the unit circle and look at where cosine is 0. That happens at pi over 2 and negative pi over 2, or 3 pi over 2 if you prefer. So that's all these asymptotes right here where the cosine is 0. So we can also find out where the tangent is 0. So these zeros right here are pretty easy to find because that's where the sine is 0. So look at unit circle. The sine is 0 at 0, so therefore there's a 0 there. At pi, the sine is 0, so there's a 0 there. So it's pretty straightforward to get the asymptotes and the zeros. Then from there, just remember the tangent goes this way, and we're going to do the cotangent. It's going to go the opposite way in a second. Might be important to think about then the period is pi. I have on the formula sheet is pi over b, because obviously we can horizontally shrink or stretch this thing. The domain is going to be all real numbers except for the asymptotes, and the range is going to be all real numbers. And the vertical asymptotes then are here, but that's something once again that we can find very easily with, like I said here. It is symmetric about the origin as well, or we can rotate 180 degrees. So here's a quick example of one then that we can graph. When we go to graph this, we know that that the period is normally pi over b, which in this case is pi over 1/2, which is really just 2 pi. So the period's 2 pi in this case. So what I'm going to do is mark 2 pi here and mark pi here. We know that the tangent function looks like this, and I know that it goes through 2 pi again as well. So halfway in between that is the asymptote. So the asymptote is at pi then. So it looks like that, and then I can just keep repeating this process. This is negative pi where there's going to be another asymptote. This is negative 2 pi where the function is going to go through that again and look like, well, that's kind of bad, but you get the idea. That's the tangent function looks like, and just keeps repeating. So at 3 pi, there's going to be another asymptote. At 4 pi, the function is going to go through that, and you get the idea. Next is the cotangent function. The cotangent function is just the reciprocal of the tangent. So for a cotangent, we're going to do cosine over sine. So now once again, you can figure out where the vertical asymptotes are because that's where the sine is 0. So that's going to be at 0. And it's also going to be at pi is when the sine's 0. So those are going to be the places where the function has asymptotes, where the bottom's 0. And where the function hits the x-axis, or where there's zeros, that's where the top is 0 for cosine. So cosine is 0 at pi over 2, and also 3 pi over 2. So you'll notice at pi over 2 and 3 pi over 2, we have zeros for the function. So once again, the domain is going to be all real numbers, except for where we have the asymptotes, which are multiples of pi, unless we horizontally shrink or stretch this. The period is going to be pi, or pi over b as I have it on the formula sheet, because we can, once again, horizontally stretch this or shrink it. The range is going to be all real numbers, just like tangent, and the vertical asymptotes are at multiples of pi, and it's symmetrical about the origin again. Okay, so then an example of graphing one of these would be this one here. This 1/3 means it's going to be a horizontal stretch of 3. So when you go to graph this, first thing is to find the period. The period is going to be pi over b again, which is pi over 1/3 for b, which is really just 3 pi. So what I'm going to do is put pi here, 2 pi, 3 pi, and the same thing back here. This is negative pi, negative 2 pi, negative 3 pi. So we know that cotangent is cosine over sine. It's the reciprocal of the tangent. So you could rewrite it like this if you wanted to, in which case, once again, we know that this 0 is an asymptote, because if you plug in 0 in for x, you get the sine of 0 over 3, which is the sine of 0 on the bottom. And we know the sine of 0 on the unit circle is 0. So this thing turns into 0 at 0. So there's an asymptote there. And if the period's 3 pi, that means there's got to be another asymptote at 3 pi, because this thing repeats, which means there's an asymptote at negative 3 pi. So then we kind of know what this thing looks like. It must then, the middle of this must be the 0, and it's opposite of tangent, so it must look like this. And it does. You can check this middle spot, which is, by the way, 3 pi over 2. If you plug in 3 pi over 2, you get cosine of 3 pi over 2 divided by 3, which the 3's cancel. And you get cosine of pi over 2, which is 0, because that's 90 degrees. So that does work. This is a rough sketch of 2 full periods of this function. Okay, now reciprocal functions like cosecant and secant look like this. They're like parabolas. And kind of the reason why, if you look at this, is because cosecant's really 1 over sine. So it's really 1 over sine. So you can tell that it's going to, whenever the sine 0 is going to be undefined, and that's these spots right here, the sine 0 at pi, and then again at 2 pi, and so on. So it's going to have these asymptotes, and then we also know it's going to reach its maximum value where the sine is 1, because the sine fluctuates from -1 to 1. So it's 1 over 1 gives you 1, and that's going to be this point right here. So at 90 degrees where the sine is 1, you're going to get your I guess, minimum for this branch, or maximum for this part down here. So it kind of makes sense. The period is going to be 2 pi over b again, just like the regular sine. The domain's all real numbers except for where the bottom's 0, except for where the sine's 0. The range is going to be all real numbers except for these values in between -1 and 1 here. And then the vertical asymptotes, we talked about those where the sine is 0, multiples of pi. And it's symmetrical about the origin, so it's an odd function. And then same thing with secant, it's 1 over cosine in this case, so you can do the same thing. It's going to have asymptotes wherever the cosine is 0, which is, multiples of 90 basically on the unit circle where x is 0. The period is going to be 2 pi over b again. The domain is going to be all real numbers except for the asymptotes, multiples of 90 degrees here. The range is going to be all real numbers again except for these values in between, -1 to 1. And the vertical asymptotes, once again, multiples of pi. And it's symmetrical about the y-axis this time, so this point reflects to over here. Okay, so here's an example then of the cosecant. It's actually easiest to write this like this: sine of x plus pi over 4. And then I think it's easiest to graph the bottom, because that's where we know that's where the asymptotes are going to be, where this thing's 0. So I think it's easiest to graph this sine function first. So this sine function is just a regular sine that's been shifted over to the left 45 degrees. So I'm going to graph the regular sine function really quickly. This is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi. Same thing back here. Now the regular sine function goes through 0, reaches its maximum at 90 degrees, goes back to pi, where this would be 1 and this would be -1, and fluctuates like this. Okay, but unfortunately we can't graph that one because we need the one that's been shifted back. So let me finish this real quick. So we need the one that's been shifted. Every one of these points needs to be shifted back 45 degrees. So I'm just going to shift all these points back 45 degrees. And then redraw this. So this point would be here. This point would be here. Okay, once you have this graphed, it's easy to see whenever this is 0, those are going to be our asymptotes. I'm going to put an asymptote here. I'm going to put an asymptote here. I'm going to put an asymptote here, and so on, because we know that whenever this sine function in the bottom is 0, there's going to be an asymptote. And then from there, it's really easy to graph. You can just graph these branches, just like this. I think that's the easiest way to graph it. Hope that helps. Oh, actually, the one thing I forgot to do is this 2 right here. That would actually make this a 2 up here. This would be a 1. This would be a 2, because that's, we know, a vertical stretch by a factor of 2. So when you plug in, for example, pi over 4, which is right here, that gives you sine of pi over 2 right in the bottom, which we know is 1. So you have 2 over 1, which is 2. So this point is 2 right here. And this is point's -2 down here for the y values. So, I'd have to relabel that really to be accurate here. Okay, the last thing you need to know is dampened oscillation, and I don't know if I'll ask you any questions about this in the test, but it's really actually easy, super easy and important, because the sine function we know oscillates like this. Well, the amplitude is what's in front here, so if we can actually put a function in for the amplitude, like this function y equals x. This function y equals x goes like this, and y equals -x will go like this then. And what that means then is the amplitude's changing. So that means that, as I get bigger in x, the amplitude's getting bigger. So what that means is the sine function is going to start getting bigger. The amplitude's going to get bigger. And if you go in the negative direction, the same thing. The amplitude's going to get bigger in the negative direction. So that's dampened oscillation. It's actually pretty straightforward. and has a ton of application in the real world because, you know, if you go over a bump in your car, you start off with a big oscillation and then it goes down like this, so you can model that with dampened oscillation. So here's an example of dampened oscillation with a sine wave. E to the x we know looks like this. You can graph it in your calculator. And therefore, if I graph the other part of it then, which is up here, I just need to graph the sine of 3x. So the sine is just going to be a wave like this. And I can pay attention to exactly what this looks like if you want. The period's 2 pi over b, and get the exact points, and in which case I have 2 pi over 3. So you can, you know, actually look at it and say, okay, well, we know the sine starts off at 0, and now 2 pi over 3 is going to be another 0, and it's got to do one full cycle in between there. So it'd be like this, you know, and you can put those points on the graph and pay better attention to it, in which case it would look more like this. And I actually graphed the e to the negative x wrong a little bit, so it's not like this, it's over here. It's exponential decay. So the dampened oscillation would look like this. Alright, I hope this helps.